Good afternoon. Welcome back to ECE 207. This is the lecture on node voltage analysis, Part B. I wanted to get us back on the correct page in terms of what we were doing and where we were doing it when we were so rudely interrupted by the computer. Let's see if we can make it through the rest of this particular node voltage analysis problem. Last time we had defined node voltages based on the nodes in the system. We identified our common node or ground node as the bottom node. We labeled that was a node, that was a node, and this was a node. We could have put another node right there, but really what you want to do is simplify the analysis as much as possible. And what we had seen is the fact that we could actually combine those two resistors in series. They are in series. Relabel that as R sub 5 bar and simply treat that as one resistor and allow us to reduce the actual number of node voltages that we need in order to analyze the circuit. We then were able to define three node voltages, V sub 1, V sub 2, and V sub 3 for this problem. We wrote KCL equations at 1 and 2, and we were just beginning to write a node voltage equation, or a KCL equation at node 3. We've already written a KCL at 1, a KCL at 2, and the approach that I'm using is to just, as a bookkeeping way to keep me organized, is I simply define currents at that node, and that allows me then to see what's going on relative to the KCL operation or strategy. For example, if I now want to do a KCL at node 3, I can see by the way that I have defined those currents that actually I have the currents going out of node 3 are I7 and I5, and the current coming in is actually the current source I sub B. And there's my KCL equation. What I now need to do is find I sub 7 and I sub 5. I sub B is a given. That's a given independent current source. But I sub 7 and I sub 5 I need to determine, and how I need to determine those are in terms of the node voltages that I have already assigned. Our strategy has been that if we want to have I sub 7 positive from node 3 to node 2, we could say we really want some voltage, let's say V sub R sub 4 hat, in that direction to give us a positive I sub 7 going from right to left from node 3 to node 2. And we can then try to remind ourselves what exactly V sub R sub 4 hat equals by simply doing this KVL expression, and we see that minus, by KVL, we see that minus V sub 2 minus V sub R sub 4 hat plus V sub 3 is equal to 0. Or what we really are wanting is this V sub R sub 4 hat formula. If we take that to the right hand side, what was left on the left hand side was V sub 3 minus V sub 2. With that voltage drop, V sub R sub 4 hat defined positively from right to left, we now know that I sub 7 is simply that voltage divided by the resistor R sub 4 by Ohm's law. And we now have then that I sub 7 is equal to V sub R sub 4 hat. That was just a defined voltage to keep us straight in terms of what we were doing. That's now dividing R sub 4, and V sub R sub 4 is v sub 3 minus v sub 2 over r sub 4. What you'll start to become comfortable with is to not have to worry about defining a new voltage v sub r sub 4 hat and writing KVL. You'll simply feel comfortable by inspection saying, oh, I sub 7, which is now going in this direction, and the way that I had defined the node voltages before tells me that I sub 7 is simply going to be v sub 3 minus v sub 2 divided by r sub 4. That same idea, after we've now replaced this with an r sub 5 bar, the voltage dropped across r sub 5 bar is simply v sub 3. If that's the case, then I sub 5 is v sub 3 over r sub 5 bar. We can now use those expressions for I sub 7 and I sub 5 in the KCL equation and come up with our third equation, which we need to solve this particular circuit. We have I sub 7, which is v sub 3 minus v sub 2 over r sub 4, plus I sub 5, which is v sub 3 over r sub 5 bar, equaling I sub b. That's now our third equation that we were after. Since we had three node voltages that we wanted to find, we need three independent equations in those three unknown values, v sub 1, v sub 2, v sub 3, and we can now solve those three equations in three unknowns to obtain the node voltages v sub 1, v sub 2, v sub 3. Once we have those, then we can find anything in that circuit that we want. But let's now, just for completeness, write the standard form of this last equation. We have no coefficients multiplying the first node voltage v sub 1. We have a negative 1 over r sub 4 scaling v sub 2, and scaling v sub 3 we have the sum of 1 over r sub 4 and 1 over r sub 5 bar. And that's equal to I sub b, and that is our third equation written in standard form. If we put all of those together, if I can find all of my different equations, we could now write all of this in matrix, in a big matrix form. Once we have it in a matrix form, you'll be able to plug that into your calculator or to MATLAB or some other numerical analysis software to solve for v sub 1, v sub 2, and v sub 3. Our first standard form equation, if I'm getting my notes right, was 1 over r1 plus 1 over r sub 2. It was minus 1 over r sub 2 times v sub 2. There was nothing scaling v sub 3, and I sub a was actually the current source going into that first node. And if you look now at your circuit, you can see for node 1, which was right here, node 1 is touched by R1, it's touched by R2. Because of that and the way that we're writing node voltage equations, we now know that if we look at the matrix structure, we have 1 over R1 plus 1 over R2. R2 was shared between node 1 and node 2, or v sub 1 and v sub 2. That's why it comes in with a minus 1 over r sub 2 in the v sub 2 location of the matrix, and I sub A was going in or helping to deliver or supply current to that particular node. The second standard form equation, we have R2 shared between V1 and V2. It's now minus 1 over R sub 2. Node 2 was touched by R2, it was touched by R sub 3, and it was touched by R sub 4. And all of those will now, if you look at this touched node 2, this touched node 2, and this touched node 2. We have node 2 right here. And that's why we have 1 over R2, 1 over R3, and 1 over R4. We're trying to sort of check our work. The resistor that was in between node 2 and node 3, or node voltage 2 and node voltage 3, was R sub 4. It then comes in with a minus 1 over R sub 4. Node 2 was not directly connected to a current source, and consequently there's nothing or no source going directly in or forcing that particular second equation. The third equation, which we just completed finding, is now 0 times V sub 1. R sub 4 was shared between V sub 2 and V sub 3. It now gives us this minus 1 over R sub 4. And V sub 3 touched R sub 4, and it touched R sub 5 bar. It was also supplied with the current source I sub B. In a matrix form then, we have this 3 by 3 matrix multiplying a voltage, giving us currents. And that's now a standard form representation of the node voltage analysis problem associated with this original circuit, where we had then defined these three voltages, or I'm sorry, these three nodes, 1, 2, and 3, and we had assigned node voltages to those nodes in order to find the unknown quantities in that particular circuit. If somebody wanted to know what is the power absorbed by R sub 2, we can find that. We can find the current going through that particular resistor. In some of our earlier diagrams, I think we had labeled that I sub 2. In this case, I sub 2 is equal to V1 minus V2 over R sub 2. The power, remember, let's say for R sub 2, is the product of voltage times current. The voltage, or it's R sub 2 times I sub 2 squared. And we could then write that as R sub 2 over, or multiplying, V sub 1 minus V sub 2 over R sub 2 quantity squared. And we're then left, if we cancel one of the R sub 2's, we have V sub 1 minus V sub 2 squared over R sub 2, and that's the power absorbed in watts by resistor R sub 2. And you could do that for all of these particular elements. If you wanted to know, we would have to have calculated or found by this analysis package, we would be told what I sub A is, we would be told what I sub B is. If those were DC or constant sources, those would simply be two numbers. I sub A could be 1, I sub B could be 2. The R's would need to be given. We would have to be told what those resistors are, and once we know all of these values in this matrix, we can simply invert that matrix, multiply it on the right by I sub A, I sub B, and we will then determine V sub 1, V sub 2, V sub 3 as voltages. Once we have those voltages determined, then these power equations, if we wanted to find those, we could calculate. V1 and V2 are now known. We can take their difference, square it. That's now the voltage drop across R sub 2. We can square that voltage, multiply it by R sub 2 and divide it by R sub 2 and obtain the power absorbed by resistor R sub 2. If we wanted to determine the power absorbed by the current source I sub B, what would we be able to say? The power absorbed, with our passive sign convention, we're saying that the power of, let's say, I sub B is going to be the voltage dropped across I sub B times the current through I sub B. And in this case, the power absorbed, since I sub B is actually going into the negative terminal before it goes through the element and ends up at the positive terminal, this will actually be a negative V sub I sub B times I sub B absorbed. Which means if we learn that P sub I sub B, let's say this is now minus, and V sub I sub B is just V sub 3, and the current is still I sub B. If it happens that V sub 3, we calculate it and we find that that's 7, and I sub B is 2, then we have minus 14 watts absorbed. Or another way of saying that is we have 14 watts supplied to the rest of the circuit by that current source, I sub B. What I want you to think about before the next lecture is how would you apply these nodal analysis techniques to analyze the following circuit. The circuit is a current source, call that I sub A, and then we have some resistors, R sub 1, R sub 2, R sub 3, and R sub 4. I want you to try to analyze that particular circuit using the node voltage analysis techniques that we've been working on today and see if you can come up with numbers, currents, voltages. You tell me what you need in order to answer a question that somebody might ask. And at that point, we will stop today's lecture and we'll pick up with the next set of topics, which will be mesh analysis.